So in this session we are going to discuss about the parallel reactions. So basically you see that in interpretation of batch reactor data, we have introduced the idea of competitive parallel reactions. So just like A simultaneously giving R, the simplest model, A simultaneously giving R and giving S. There are two parallel reaction pathways, right, of order N1 and rate constant K1 for the first, and whereas it is of order N2 and rate constant K2 for the second. So a topic is design of parallel reactions. So you see A giving R and simultaneously giving S. Let us say this is the desired product. Whereas this one is undesired. So we have to maximize the production of R upon tuning the concentration and temperature. Let us consider this rate constant K1 and order N1, here the rate constant K2 and order N2. Or we may think of a reaction A plus B giving R and S directly. Okay. So, okay, let's not complicate. Let's go it by A first. Next we will introduce this A and B. So here minus of RA in pathway 1, which is according to the stoichiometry is rate of formation of RR, is K1 into Ca to the power N1, whereas minus of RA for 2, which is RS, is K2 into Ca to the power N2. So if I think of these two rate ratios, which is RR by RS, and that is DCR by DCS, equal to K1 by K2 into Ca to the power N1 minus N2. Now further, if I go for introducing this Arrhenius model to decipher the temperature dependence, we can write K01 by K02 e to the power minus E1 minus E2 by RT into Ca to the power N1 minus N2. Now you think that there are certain conditions, or rather inference. Number 1, if N1 is greater than N2, Ca should be kept as high as possible. Right. So for continuous flow reactor, we know that we have previously discussed that we can maintain the concentration high if within the scope of ideal reactors only, if it is a PFR, or that is the plug flow reactor. Okay. So we may use a PFR or Cstrs in series, because we know that as we go on adding Cstr, hooking up Cstrs in series, multiple numbers of Cstr, its behavior tends to that of PFR. Okay. So next, else if N1 is less than N2, Ca should be kept as low as possible. So here we may use CSTR, right? A single CSTR, a single large CSTR, right? So next issue is about temperature. If E1 is greater than E2, E1 is greater than E2, then we should maintain a high temperature. Maintain a high temperature. Else, if E1 is less than E2, we should conduct the reaction at low temperature. Right. So that's for a single reactant having two parallel pathways. Now let's go for what we have intended to discuss initially, that extension of these inferences for a bimolecular second order, or maybe this bimolecular reaction, right? So A plus B giving R giving S, this is desired product, this is undesired. So we have minus, so this is pathway 1, this is pathway 2. So minus RA1 is equal to K1 Ca to the power A1 Cb to the power B1, and minus RA2 is K2 Ca to the power A2 Cb to the power B2. So we have this dCr by dCs is equal to Rr by Rs. It's equal to minus of this Ra1 by minus of Ra2. It's equal to K1 by K2 Ca to the power A1 minus A2 into Cb to the power B1 minus B2. Right. So finally it's coming to be dCr by dCs in terms of temperature as well, K01 by K02 e to the power minus E1 E2 by RT Ca to the power A1 minus A2 Cb to the power B1 minus B2. Right. So here you see we can draw certain inference, or rather recommendation. Number 1, if A1 is greater than A2, B1 is greater than B2, keep Ca and Cb high. Right. So here in batch mode we have to think of, we are adding A and also we are adding B simultaneously in equal amount, such that the concentration is pretty high. So here what we have to do, add A and B one at a time. So this is the batch mode. Right. And in continuous mode we must use a PFR, and we should deliver the A and B at high concentration at the inlet. Next, if A1 is less than A2 and B1 is less than B2, Ca and Cb should be kept low. Right. So here we should go on adding A and B simultaneously in small amounts. A and B. So here A and B we have to add A and B slowly. So in continuous mode, it should be a single large Cstr. So here A and B being delivered, and here from we draw the product. Right. Now next is if any A1 is greater than A2, just the opposite for the two reactants. Here it was having a kind of parity. Right. Now just the case is A1 greater than A2, but B1 is less than B2. Third, if A1 is greater than A2, B1 is less than B2. Keep Ca high and Cb low. And how we can do that? Here in batch mode or in a basically semi-batch mode, initially pure A, and in that you add B in drops. Add B in small amounts. Right. Whereas in continuous mode, we should deliver A and there may be side-wise entry of B throughout the entire length of the reactor. Right. So it is, we can think of a single PFR with side entry. So it is PFR with multiple side entry, and we can alternatively have a multiple Cstr, right, like here I am describing this Cstr cascade, and here we have A in high concentration, it goes to here, it goes to here, and in each we are adding B by small amount. Right. So that's the basic idea. So you should go on adding B. So Cstrs in series with individual feeding system for B in each reactor. Right, we should feed that B individually in every reactor, and that's basically the optimized design for this specific stoichiometry or order, not stoichiometry, it's the order. A1 is greater than A2, B1 is less than B2. Okay. So with that, we have got a qualitative understanding that how to maximize the desired product in a competitive parallel reaction pathway. So that we can quantify upon introducing a quantity called yield, right. So we have to understand what, so quantitative analysis of competitive parallel reactions. Concept of yield. Right. It's of generally two types. One is instantaneous, yield, and this is overall yield. Capital Phi. Right. So instantaneous yield, how it is defined? It is defined as dCr by minus dCA. Okay. Moles of R formed divided by moles of R reactant. So it is moles of R, the desired product, formed by moles of A reactant. Okay. Now, for example, we can think of a reaction A giving R giving S, right? Or this is K1, this is K2, this is N1, this is N2. Then phi expression will be K1 Ca to the power N1 divided by K1 Ca N1 plus K2 Ca N2. Right. So that gives you the instantaneous slope of this line, Cr versus Ca. Okay. Now, contrary to that, we have another this overall yield definition. And how we can describe that overall yield? Let's see. So, overall yield, capital Phi, is equal to final amount of R divided by the amount of A reactant. Okay. So, there is a relation between capital Phi and small phi. You see, this dCr is equal to minus phi into dCA. So, if I integrate, considering this initial amount of R is 0, then we will get this is from Ca0 to CAF phi into dCA. Right. So, capital Phi is equal to minus 1 divided by Ca0 minus CAF integral Ca0 to CAF phi into dCA. So, this is the relation between overall yield and instantaneous yield or fractional yield. Right. So, you see that this is the relation between overall and fractional yield. Now, the thing is, we will try to apply it for the ideal reactors like PFR, CSTRs and PFRs in series. CSTRs in series. So, for CSTR. Now, in CSTR everywhere the concentration is same. So, phi overall it's equal to minus of 1 divided by Ca0 minus Cf, and this is simply constant because it is to be evaluated at Cf multiplied by Ca0 minus Cf. Caf minus Ca0. Right. So, what do we get? Phi m stands for MFR of CSTR. This m stands for MFR. It's equal to instantaneous yield evaluated at Ca is equal to Caf. So, next it is the PFR. Now, in PFR you see this phi changes. So, phi p, capital Phi p is equal to minus 1 Ca0 minus Cf, this Ca0 to Cf integral phi dc. Okay. So, that will be the expression for phi p. So, this is basically, this phi is nothing but capital phi at Ca. Okay. So, you can write it as minus 1 divided by Ca naught minus Caf integral Ca naught to Caf capital phi m at Ca dCa. This is simple algebra by which we can get that. Here small phi and capital phi are same, but small phi is to be evaluated at Cf. So, here if we write that capital phi m at Ca, which is nothing but equal to small phi, so we can integrate it and get a relation between them. So, on the other hand, you see that phi p and phi m, they are related by this. So, if I take the derivative, so d phi p dCa, right, d phi p dCa definitely to be evaluated at Caf, it is equal to phi m at Cf, right, phi m at Cf. Because this integrated value will cancel out finally, taking the derivative. So, yeah, we will have this and yeah, phi p by phi m at Cf, phi m del phi p del Ca yeah, but there is a point that this is not going to cancel out. So, that divided by Ca naught minus Caf will also be there. So, that's not very working equation. Basically, the working equation will be this and this definition. We will see it later. So, but this is a basic understanding regarding the how this yield and these concentrations and of the desired products, they are related to each other. So, with that we can also think of Cstrs in series, right. So, in a Cstrs in series, what will happen and what will be the relationship between the capital phi and small phi, that we have to understand. So, you see this is Cstrs in series. So, here Crn, the final, will be equal to Crn minus Crn minus 1 plus Crn minus 1 minus Crn minus 2 and finally Cr1 minus Cr0, which is basically 0, right. So, this one will be equal to phi 1 at Crn into Can this let us see what's happening, this dCr by dCa minus is equal to phi. So, Cr is equal to, this phi is constant, right. So, this phi for the reactor N into change of concentration with a negative sign. So, that is Can minus 1 minus Can, something like that. Yeah. So, Can minus 1 minus Can plus the second phi 2, this is Can, right, Can minus 1 into Can minus 2 minus Can minus 1, and in this way finally phi 1 at Ca1 into Ca0 minus Ca1. So that's the relation for phi and the final concentration. Okay. So if you think of this graphical interpretation, we can understand that this phi versus Ca, if this is the plot, this is Ca0, this is CAF, right? Yeah, this is CAF. So CRF is equal to the area under the curve. So this is equal to CRF. So for this is for PFR. Now for MFR, phi, this is CA, this is CA naught, this is CAF. Now this area, because this area is equal to phi at CAF into CA naught minus CAF, which is the CRF for this single CSTR. Now for multiple CSTRs, what we have discussed just right now, the curve will be like this. This is CA0, CA1, CA2, and finally CAN, CAN minus 1. Right? So this plus this plus this plus this, these area are to be added. Right. So that's equal to CRF, which is summation of what we can write as phi I CAI into CAI minus 1 minus CAI. So I equal to 1 to n. Right. So you see, this gives you a similitude that infinite number of CSTR is also equal to a PFR. Right. Because if you go on adding this area, and if this width of individual area becomes differential, it will be nothing but the area under the curve. So from this perspective of fractional yield, or in general the yield, we can also justify that infinite numbers of CSTRs in series give rise to a PFR. So with this understanding, we will solve some problems. Let's see. Okay. Two demonstrative problems now we are going to discuss in this chapter of field, and we will solve some more problems to understand the idea that how to deal with this competitive parallel reaction. So yield formalism, you have to note that this is specifically valid for competitive parallel reaction, right? So what is the problem? Consider a reaction. So this is the example. A plus B giving R, giving S, K1, K2, and dCr dt is given as Ca to the power 1.5 into Cb to the power 0.3. Right. This is in mole per liter per minute. And here it is dCs dt, that's equal to Ca to the power 0.5, Cb to the power 1.8 mole per liter per minute. So obviously K1, K2 are 1, both. So 90% conversions, what is the problem statement? For 90% conversion of A, find the concentration of R in the product stream. CRF, XAF is this, what is CRF? Right. In PFR and number 2 in MFR. In both cases we have to find out. And what is the feed? Equal volumetric flow rate of A and B streams are fed to the reactor, and each stream has a concentration of 20 mole per liter. So V1 Ca1 equal to 20 mole per liter here, or VCA1 here, VCB1 or CB2 is 20 mole per liter. Right. So obviously here CB1 is 0 and here Ca2 is 0. Right. So Ca0, what we should use is V1 Ca1 divided by V1 C or VCA1 divided by VCA1 divided by 2V. So Ca1 by V. So we are getting what? Ca1 by 2. So it is 10 mole per liter, and same as Cb0, which is V Cb2 divided by 2V, Cb2 by 2, 10 mole per liter. So that's the initial concentration. Now if I think of PFR, what is CRF? CRF is minus of 1, Ca0 minus CAF, integral Ca0 to CAF, phi into dC. Right? Now what is phi of R with respect to A? So this is a standard notation we use. This is Ca to the power 1.5, Cb to the power 0.3 divided by Ca to the power 1.5, Cb to the power 0.3 plus Ca to the power 0.5, Cb to the power 1.8. Right? So if I divide this equation by Cb to the power 0.3 and Ca to the power, divide this numerator and denominator, Ca to the power 0.5, Cb to the power 0.3. Right. So numerator becomes here the Ca divided by Ca plus Cb to the power 1.5. Correct? Now there is a understanding that what is Ca? Ca is equal to Ca0 into 1 minus Xa. Right. What is Cb then? Cb0 minus Ca0 into Xa, because 1 mole reacts with 1 mole. Right. So Ca0 into 1 minus Xa as Cb0 is equal to Ca0. So this is equal to nothing but Ca. As these initial reactants were given in stoichiometric proportion, Cb and Ca must be same. So phi of R by A equal to Ca divided by Ca plus Ca to the power 1.5, which is 1 divided by 1 plus under root of Ca. Right? Yeah. So, phi p or CRF directly. CRF not, this is not CRF, sorry. This is phi p, right. So, CRF is equal to phi p into Ca0. This is Ca0 by Caf. So, this is minus of Ca0 to Caf small phi r by A dc. And now what is Ca0? 10, and what is the conversion? 0.9. So, Caf is equal to 1. Why? Because it is 10 into 1 minus 0.9. Next, we have 1 divided by 1 plus under root of Ca dCa. So, that we have to integrate. We can change the limit to 1 to 10 dCa divided by 1 plus under root of Ca. Now, Ca if we consider as x square, then dCa is equal to 2x dx. So, we have 2x dx divided by 1 plus x. Right. Now, x here it's 1 and here it will be 100. So, you solve and you will get CRF. Right. You will get that CRF. Yeah. So, that is the solution of CRF for PFR. Now, if we go for repeating the same problem in case of CSTR, what will be the change? So, here CRF for PFR outlet, it is coming to be 1.47 mole per liter. Right. Now, here this capital phi, or rather directly we can write CRF is equal to small phi Ca equal to Cf into Ca0 minus Cf. So, this is 1 divided by 1 plus under root of Ca at Cf, which is equal to 1, multiplied by 10 minus 1, which is basically 9. So, this is 1 divided by 1 plus 1 into 9, so which is 4.5 mole per liter. Right. So, it shows that MFR is giving you much better yield compared to that of PFR. Okay. So, next solve another problem of similar type. See, let us consider the decomposition of A with Ca0 is equal to 2 only. Find the maximum expected Cs. Cs max we have to find out for an isothermal operation in MFR and PFR. Right. For the reaction A giving R, giving S, giving T. Right. This rate RR is 2C, this RR is Ca square, Rs is 2Ca and RT equal to 1. So you see for MFR, Cs, or rather first let us calculate phi of Sa, which is 2Ca divided by 1 plus 2Ca plus Ca square, giving you 2Ca divided by 1 plus Ca whole square. Right. So CSF is phi Sa at CAF into Ca naught minus CAF. So this becomes 2 CAF divided by 1 plus CAF square into this is 2 minus CAF. So this is the expression of this concentration, and we have to maximize this. So we will take the derivative of the CSF with respect to CAF and set it equal to 0. So DCAF, what will be the case? The denominator is 1 plus CAF whole to the power 4. The numerator, it is basically equal to what? 4 CAF minus 2 CAF square divided by 1 plus CAF whole square. So the numerator becomes 4 minus 4 CAF into 1 plus CAF whole square minus 4 CAF minus 4 CAF square into 2 into 1 plus CAF, and that we have to set equal to 0. So you see 4 1 minus CAF into 1 plus CAF square minus 4 CAF into 1 minus CAF, right? Yeah, and here it will be 8 because 4 into 2 is 8. So 1 plus CAF equal to 0. So this cancels out, this also cancels out. So 4 into 1 plus CAF minus 8 CAF equal to 0. So 4 here 4 CF minus 8 CF, so this is 4 CF. So CF equal to 1. That is the optimal concentration. So if CF is equal to 1, CF is equal to Y1, here it is given half. Oh, this is 4 minus 2. So you have done a mistake. No, here it is 4. So this one must be 2, right? This one was 2. Yeah. So it will little bit change. 4 1 minus CF 1 plus CF whole square minus 2 CF 1 minus CF into 2 1 plus CF. This is 2 minus CF equal to 0. So this and this cancels out, and 4 cancels out. So this is 1 minus CF square minus 2 CF plus CF square, that is equal to 0. So this cancels out, so CF is equal to half. So CSF is equal to 4 into half minus 2 minus 2 into 1 by 4 divided by 1 plus half whole square. So that is 2, 4 into half, 2 minus half, 3 by 2 whole square. So that is also 3 by 2, right. So that is 3 by 2 whole square. So that is 2 by 3. So that's the final concentration of CSF, okay, in MFR. Now if I repeat the same procedure for PFR, what we will get? Here you see this for PFR, phi P is equal to CRF divided by CA0 minus CAF is equal to minus 1 CA0 minus CAF into CA0 to CAF phi SA DCA. So this is S. So this getting you CFF equal to minus of CA0 to CAF phi of DCA, which was equal to what? 2CA divided by 1 plus CA whole square DCA, and CAF is equal to 2. So we have to integrate it. So you have to integrate, integration you can perform. So we'll get a function of CAF basically, because 2 is here as constant. So if you put the limit, you will get a function of DCF. So next you have to take the derivative, right, which is f prime CAF equal to 0, and solve for this CAF optima, which will be coming to be 0, right, which will be coming to be 0. You can check it out, and CSF is equal to 0.867. Yeah, 0.867. So that's the basic understanding of this yield. So what we have followed here in the second problem, we have solved for this fractional yield expression. We have got this outlet concentration expressed, outlet concentration of the desired product expressed in terms of the reactant concentration at the outlet, and from there we are taking the derivative to solve for this optimal concentration of CF and the maximum concentration of the desired product. So that's all about this yield formalism. So next we'll think of any possible multiple reaction, and our objective will be there that how to optimize the time, right, the space time, so as to maximize a specific product, the concentration of the specific product at the outlet. So this may include mostly series reaction, because only, or series parallel reaction as well, because we already know how to deal with competitive parallel reaction. So the approach what we are going to study is much more generalized one, right. It is based on entirely on this fundamental balance, and from this balance we will try to solve for this optimum space time. So the first we are going to discuss about, this is the topic, multiple reaction in continuous reactor, optimization of space time. Right. So let's say a series reaction, A giving R giving S. Solve first order reaction, K1, K2. and it's taking place in a CSTR, and R is the desired product. So it's taking place in a CSTR. We are giving CA naught, CR naught equal to CS naught equal to 0. Volume flow rate is V naught. Right. So if I write the balance component balance equation for R, if I write that, what I will get? Input equal to output plus accumulation plus disappearance by chemical reaction. So input of this R. So for here, let's write for the desired product. That is R. So input is 0 as there is no concentration. Output is V naught into CR. Now disappearance by chemical reaction, disappearance, so first it will be K2Cr minus K1Ca. So that is the net disappearance rate, specific rate multiplied by the volume. Okay. So if I divide the constant volume system, consider constant volume system. So 0 equal to Cr plus K2Cr minus K1Ca whole bracket tau. So K1Ca tau is equal to Cr 1 plus K2 tau. So Cr is equal to K1 tau divided by 1 plus K2 tau into Ca. So we have this unknown, right? How this is dependent on the space time that we don't know, so we have to solve it as a function of tau, and that we have to substitute here. So obviously we have to write balance equation for A. So input is V naught into Ca naught, output is V naught into Ca, disappearance by chemical reaction it's R1 into Ca into V. So if I divide the entire equation by V naught, you will get Ca naught equal to Ca plus K1 Ca tau. So obviously Ca naught equal to Ca is equal to Ca naught divided by 1 plus K1 tau. Therefore, we have Cr here, it's equal to K1 tau divided by 1 plus K2 tau into 1 plus K1 tau into Ca naught. So you have to maximize this Cr at the outlet, and we have to fix the respective optimum tau. So dCr d tau Ca naught denominator will be 1 plus K1 tau into 1 plus K2 tau whole square. So it is 1 plus K1 tau 1 plus K2 tau minus K1 tau. Here it will be K2 into 1 plus K1 tau plus K1 into 1 plus K2 tau. Right. So what is the expression? Ca naught 1 plus K1 tau into 1 plus K2 tau, and it will be obviously overall whole square. So it is 1 plus K1 tau plus K2 tau K1 K2 tau square minus here K1 K2 tau K1 K2 tau minus K1 square K2 tau square, this one, minus here. Here I think it will be K1, right. So it is K1, K1 square, K1 K2, K1 square, K2 tau square. So here it will be K1 square tau, K1 square tau minus, so here it is all minus K1 square, K2 tau square. So K1 square, K2 tau square. So let's check whether anything is cancelling out or not. K1 square tau, right? So K1 square tau. So this cancels out. Yeah. K1 K2 tau, K1 K2 tau, that also cancelling out. K1 square K2 tau square, K1 square K2 tau square, that also cancel out. So we have K1 is equal to, because this is set equal to 0, it is K1 square K2 tau. So tau will be under root of K1 K2. So tau will be under root of 1 by K1 K2, and that is basically the tau optimum, which will maximize the desired product, right, which is R. Now the same if we do it for PFR, I think we already know the answer, because the PFR with constant volume system and batch reactor with constant volume system, they are having the same governing equation, right, and the tau optimum we can actually calculate as 1 divided by K1 K2 log mean, as we did it for batch in this topic, interpretation of batch reactor data. But how to generate the governing balance equation here for PFR? So this is V equal to 0, or rather tau equal to 0, that is tau. This is V equal to 0, that is V, and as it is a distributed parameter model, the PFR is a distributed parameter model, as there is a change of concentration along the axial direction. So we will consider a differential volume element between V to V plus dV, or alternatively between tau to tau plus d tau. Right. So here we have V naught, CA naught, or sorry, CA, CR, and here we will have CR, CA at V, and here CA at V, CR at V plus dV, etc. Right, and the V naught. So let's write the balance equation for R. So inflow is V naught into CR at V. Outflow is V naught into CR at V plus dV. Right. Accumulation is 0 because it is steady state. Disappearance by chemical reaction K2Cr minus K1Ca into the volume, which is dV. So if I divide the entire equation by V naught, we will write that Cr at tau is equal to Cr at tau plus d tau plus K2Cr minus K1Ca dV by V naught, which is d tau. So you see that if we shift this on this side and divide this by d tau, so we'll get dCr d tau is equal to K1Ca minus K2Cr, which was same as the batch, and that shall be dCr dt is equal to K1 Ca minus K2 Cr. Right. So the equation remains same. Now here we have A. So we have to find out the respective differential equation for A itself. So here balance for A, it will give you what? V naught into Ca at V, V naught into Ca at V plus dV, accumulation is 0, disappearance by chemical reaction K1 Ca into dV. So dividing it by V naught, we get Ca tau is equal to Ca tau plus d tau plus K1 Ca d tau. So obviously we get minus of dCa d tau is equal to K1 Ca, which indicates that Ca is equal to Ca naught into e to the power minus k tau. So if I substitute it back, dCr d tau plus K2 Cr is equal to K1 into Ca naught into e to the power minus k tau, and we solve it with a condition, initial condition, that tau equal to 0, Ca equal to Ca naught, right, and from there we can get this dCr d tau set equal to 0 and solve for tau optimum, which will be coming to be 1 divided by K1 K2 log mean. Right. So the strategy here, what we have to note, it's pretty simple, but at the same time we have to understand that here for PFR we have to be very cautious also for CSTR regarding this balance equation. So always write the balance equation for the desired compound, and there you will see some unknown concentration terms are appearing. Just like here we have an unknown concentration term Ca. Now write the balance equation for that specific component, right, in order to express it in terms of known concentration, substitute it back, so you get an explicit equation, then solve it and take the derivative and all. So that's the procedure. So let's solve another example of series reaction, but it is a first order reaction followed by a zero order reaction. So here it is A giving R giving S. So this is K1, K2, N1 equal to 1, N2 equal to 0. Right. Now solve it for batch or plug flow. Right. So obviously we will have this Ca will get Ca naught into e to the power minus k1 tau. It's obvious, right? And dCr dt, dCr d tau plus k2 or equal to k1 into Ca naught into e to the power minus k1 tau minus k2, right? So if you integrate if you simply solve this equation upon integrating it, so Cr is equal to k1 Ca naught integral 0 to tau e to the power minus k tau d tau minus k2 tau. Yeah. Minus k2 tau. So K1 Ca naught here e to the power minus k tau by minus k. So 1 minus e to the power minus k tau, this is I think K1, so divided by K1, yeah, minus K2 tau. So this cancels out, so we get Cr is equal to Ca naught 1 minus e to the power minus K1 tau minus K2 tau. So dCr d tau is equal to e to the power minus K1 tau into K1 minus K2 equal to 0. Right, into Ca naught. Ca naught into e to the power minus K1 tau divided by this K2 tau and all. So you see, Ca naught into e to the power minus K1 tau optimum into K1 here, right, equal to K2. So ln of K1 into tau with a minus sign equal to ln, this will be ln, so it will be minus K1 tau. So ln of K2 divided by K1 into Ca naught. So tau star is equal to 1 by K1 ln of K1 Ca naught by K2. So that's the optimal concentration. So if you solve for this Cr max, I am not detailing the algebra. So it is 1 minus K, which is K1 Ca0 by K2 this is K2 by K1 Ca0 into 1 minus ln of K2 by K1 Ca0. Right. So that's the optimal concentration of R. And graphically, we can interpret that as concentration of A will be decreasing like this, right. Concentration of R will be increasing. This is tau star, this is Cr, this is Ca, and concentration of S will linearly increase and finally settles down. So this is Cs, and that's tau. So this was a gate problem, I think. That if a first order is followed by a second order reaction, so it will be like this. Now let's solve another problem. This is an elementary liquid phase series parallel reaction, right? And we have to optimize the space time. This is exactly a gate problem. Optimize the space time for Cstr. So the reaction, see, elementary liquid phase reaction, A giving B giving C and A giving R, right, is to be carried out in a Cstr. So RR prime K prime Ca and Rb prime is Kca minus Kcb. Right. So feed is pure A. Feed is pure A and the reactor is Cstr. So which results in maximum exit concentration of B. So you have to maximize B. Right. So for B, you see the inflow is 0, outflow V0 into Cb, right. Disappearance by chemical reaction. Here you see that RR, this is K prime, this is K, this is also K. So disappearance by chemical reaction, it is KCb minus KCa whole bracket into V. So we have 0 equal to Cb plus KCb minus KCa into tau. Right. So KCa tau is equal to 1 plus K tau into Cb. So Cb is equal to K tau divided by 1 plus K tau into Ca. So very similar to the typical series reaction. Right. Now for A, we have inflow V0 into Ca0, outflow V0 into Ca, disappearance by chemical reaction Kca plus K prime Ca whole bracket into this V. So Ca0 equal to Ca plus K prime whole bracket Ca into tau. So obviously Ca is equal to Ca0 divided by 1 plus K prime whole bracket tau. So we have Cb is equal to K tau Ca0 divided by 1 plus K tau into 1 plus K prime whole bracket tau. So you already know the answer considering this is K1, this is K1 and this is K2. We already know, just we have solved that optima is 1 divided by under root of K into K plus K prime. So we have tau star is equal to 1 divided by under root K plus K prime. So that's all about the multiple reaction. In the next session we will discuss the elementary idea of catalysis. Thank you.